Hi everyone. So in today's tutorial sections, I will still continue a few questions related to the Gauss law and then followed by the questions of the potential difference. Alright. Okay, so this is a question actually in your PowerPoint slide. So we have tried the first question in our tutorial week 3. So now we are going to try these questions. Okay, so if a point charge, okay, the value is equal to 90 microcoulomb is located at the center of the spherical shell with radius A, and the surface charge density is negative 8 microcoulomb per meter square. Find the D everywhere when the A is equals to 1. So now let's look at these situations. So you have a point charge. Okay, so this is a positive point charge located at the center of the spherical shell. Okay, so you have a spherical shell. Okay, so this is your spherical shell, right? Okay, so the spherical shell has a radius of A. Okay, and the rho s is given as negative 8 microcoulombs per meter square. Find the D everywhere. Okay, find the D everywhere means that, okay, you need to find out the D, okay, in this region and in these regions. Okay, so for this first region, it is the region where the R is less than the A. And for this second region, okay, it is the R greater than A. Alright, so you need to find what are their D. Okay, what are the D? Okay, clear about these questions. So we go to the case for the R less than A. Okay, so this is the regions, okay, where we want to find the D, right? We want to find the D everywhere over here. Okay, so the first step is we have to construct a Gaussian surface. Okay, so I construct a Gaussian surface. Okay, Gaussian surface over here. Okay, so what is Gauss law? Gauss law says that the total flux coming out from the Gaussian surface will be equals to the total charge that is enclosed by the Gaussian surface. So this is your Gaussian surface. Okay, let's see where is the direction of our flux. You have a positive charge, so the positive charge is moving, the flux line is moving outward, right? It's moving outward. Okay, so the direction of the flux is in the R directions. Okay, in the R directions. Okay, so the Q over here will be the Q enclosed by the Gaussian surface, which is this Q. Okay, which is this Q. Right, so let's write down. Okay, so this is a dx, so you will have the double integral your d in the R directions, dot product with the R square sine theta d theta and dv. Okay, I think you're used to this statement already. Okay, because we tried a few exercises in our tutorial week 2. Right, so the interval for the d theta will be from 0 to pi, and this one will be from 0 to 2 pi for the phi. And then on the other hand, we have the Q, right? What is the Q that is enclosed by the Gaussian surface? So you can see this thing very clearly. The Gaussian surface, okay, only enclose one charge, okay, that is 90 microcoulombs. Okay, so you write down 90 microcoulombs. Just write down here, 90 microcoulombs. Okay, so you can start simplify it, and here you will get d r square 4 pi, right, equals to 90 micro. 90 micro. Okay, so your d would be, okay, your d would be 90 micro divide 4 pi r square. Okay, so this one is your value. If you want to include the directions, then it would be r. Okay, so you can do this, the 90 micro. Okay, so you get 7.16 over r square. This is the directions. And the unit of the electric flux density, the D, is equals to, this is microcoulomb per meter square. Alright, so in this case, maybe someone will be asking why we didn't consider the charge, okay, the charge on the spherical shell. Okay, this is because you look at the Gaussian surface, it didn't enclose, okay, it didn't enclose the spherical shell, it only enclosed one charge. So that's why in this case, we didn't consider the spherical shell, we only consider the charge, right? Okay, so this is the answer when the R is less than the A. Then we move forward to the next region when the R is greater than A. R is greater than A means that is this point, alright? This point outside the spherical shell. So the first step is still the same thing. You need to construct a Gaussian surface. Okay, and this one will be your R. You see your R is greater than the A. Okay, go back to the Gauss law. Okay, so the total electric flux that coming out from the Gaussian surface will be equals to the total charge that is enclosed by the Gaussian surface. So now let's examine the direction of the flux that coming out or going inside, okay, the Gaussian surface. Look, in this case, your spherical shell is has a negative charges distributed. And you see this is a negative charge, right? So it also means that the flux, okay, that pass through the Gaussian surface will be inward like this. It will be inward. Right. So the D will be in the negative R directions. Negative R directions. Okay. Right. So over here, what we will do is we write down the same thing. And our D is in the negative R directions. Okay. Dot product with the R square sine theta d theta d phi and unit vector R are the directions. Okay, so I think I don't need to explain this. You already know. Okay, let's look at the right hand side. You have the Q. So look again, your Gaussian surface, the blue one. Okay, so in this case, you can see that it actually enclosed two charge components. The first one is the point charge at the center. And the second one is this, okay, is the spherical shell, this one. So this is the second charge component that is enclosed by the Gaussian surface, right? So we need to put them both here. So it will equals to the summations of 90 microcoulombs and also the surface charge, okay, the charge from the spherical shell. So you need to perform these operations. Right. Yeah, these operations. Because the Q equals to rho x dx. Okay, so the dx here, you are going to select one coordinate systems. Okay, so you will be selecting the spherical coordinate. Then it will be r square sine theta d theta d phi. Alright, interval from 2 pi. Okay, so this one will be the interval. Right, so this one will be the R of the spherical shell. The R of spherical shell. Okay, R for the spherical shell. Right, look at the right hand side. So here you will have a negative d r squared 4 pi, right? And over here, you will have a 90 micro plus, okay, so you will have a rho x r squared and 4 pi. Okay, so the question mentioned that, okay, the A is equals to 1. Let's see. Find the D everywhere when the A is equals to 1. Okay. So when the A equals to 1, meaning that this one we're going to replace it with A squared, which is equals to 1. Okay, and the rho s is given. Okay, rho s is given. The rho s is negative 8 micro, right? Negative 8 micro. Am I right? Yes. Okay, so you can calculate the value now. Over here, so you have a 90 micro minus 8 micro so this one will be negative 1.05 times 10 power negative 5. Okay, and then your D, okay, your D would be negative 1.05 times 10 power negative 6 over 4 pi r squared. Okay, so you get, so you have a negative here, right? So you have a negative so you get 8.38 times 10 power negative 7 over r squared, D. Okay, so this is the magnitude. Okay, if you want to consider the directions, it will be negative r. Okay, it will be a negative r. So this one will be your D outside the spherical shell, where you have to consider two, okay, charge components. One is a point charge, the other is a surface charge from a spherical shell. Right? Alright, we look at the next questions. Okay, this is a charge distribution in free space that has the rho v equals to 2r. Okay, 2r. And I think the r is actually the capital letter R. Okay, 2r. Okay, so for the r in between 0 to 10 meter. So, and 0 otherwise. Okay, so it means that only when the r is in between 0 to 10 meter, okay, it has the rho v, it has the volume charge density. Now you have to determine the E at 2 meter and also 12 meter. Okay, so this is obviously a volume structures, okay, that has the rho v, okay, which is equals to 2r nanocoulombs per meter cube. All right, and then, okay, So in between 0 to 10 meter, okay, that is the 10 meter, okay, the rho v is equals to 2r nano. Okay, you have to find the r at 2 meter. Okay, 2 meter maybe somewhere here, 2 meter. And also 12 meter. 12 meter is something further away. Alright, so now let's look at this case to find the electric field when the r is equals to 2 meters. So let's derive the equation for this case. So first of all, we must have our we must apply the Gauss law. Okay, that is the total flux coming out from the surface will be equals to the total charge that is enclosed by the surface, right? So this one is R, okay? So in this case, our R is less than the 10, it's less than the 10, right? So we apply this. Okay, so our D will be in the R directions, right? Okay, so the flux coming out, okay, from the surface. Okay, so this one will be the flux coming out from the surface. Okay, from the Gaussian surface. Right. Okay, then dot product with the R square sine theta, d theta, d phi, and R. Okay, on the other hand, you have a Q that is enclosed by the Gaussian surface. You could find it by integrating the rho v, okay, R square sine theta, dr, d theta, and d phi. Okay, so this one would be the R, okay, that you want to find. Okay, the R that you want to find is electric field. Okay, so it will be 0 to R, right? 0 to pi and 0 to 2 pi. Okay, so let me solve for the right hand side. You will have a rho v, then R cubed over 3, right? This is 0. And then you have a 4 pi. Okay, you can solve it yourself. Okay, and for this part, you will have this equals to 1, then you have the d r square and 4 pi. Right, so you can cancel this part. Then your d, okay, will be equals to, oh yeah, I forget the rho v over here. The rho v is 2r, right? Yeah, I should specify here. It's a 2r. So meaning that you have 3r. So this one will be 4. Okay, when you integrate. Right, or maybe I will write like this. I will just combine them to make it 2r cubed. Okay, so when you perform the integration on this r cubed, you will get r power 4 over 4. Okay, right? Okay, so here it will be, so will be r4 over 2, right? And then you have r square. All right, so here you have a r2, okay, r power 2, r power 2 over 2, and your e, okay, this one you can put the directions. It will become r square over 2 epsilon naught and r. So when your r is equals to 2 meter, okay, so you can replace here 4 over 2 epsilon naught. I think I forget the yeah, nanocoulombs, nanocoulombs, sorry. So here we still have nanocoulombs, nanocoulombs. Okay, so it is 1 nanocoulombs. So we have nano here, nanocoulombs, nano. So 4 nano divide, so is equals to 225.88. Okay, in the R directions. Right, 226. So in this case, even though the derivations is very similar to the derivation that we did earlier, that is to find the rho v, okay, but because the rho v, okay, has the variable of r, so when you perform the integration at this part, okay, the equation will become different. So if you use the equations in the book or in the PowerPoint that we have defined earlier, you cannot get the answer. You cannot get the answer. Okay, so meaning that you have to derive yourself one more time, so get this answer. Okay, we look at the next question. Is when the R is equals to 12. So R equals to 12 is actually outside the volume structure. So it's over here, right? Outside. Outside the volume structures. So we are going to repeat again the same thing. Okay, going to derive the equations ourselves. For the case R is greater than the 10 meter, okay, we start from here again. Okay, so basically this part is the same. The D is in the outward directions. Okay, then you have R square sine theta d theta d phi. Okay, whereas the Q, you have the triple integrals, right? And the rho v is equals to 2r nano. Okay, then you have a R square sine theta dr d theta and d phi. R will be from 0 to 10. Okay, even though the value is 12, but you have to put 10. Okay, because that is the size of your volume structures. Okay, and this one is from 0 to pi, 0 to 2 pi. Oh yeah. Okay, so here you will have a dr square 4 pi. Okay, just like usual. And on the other hand, you will have 4 pi. Okay, you will have a 2 nano there. And this r cube, okay, you're going to perform integration 0 to 10 r cube dr, right? Okay, this thing will settle when you integrate this one and this one. Okay, so you can press calculator, r cube, and then 10, and then 0. So you get 2,500. Okay, 2,500, yeah? Okay, right. So now try to solve the equations. So it will be 2 nano multiply 2,500. So you get 5 micro. Okay, 5 micro divide r square. And your E will become 5 micro divide epsilon naught r square. Right? So if you want to put the direction, you can put the directions. Okay, so when the R is equals to 12, okay, so you replace with 12. 12 square. Okay. So you get, you get 3921.59. Okay, this is the directions volt per meter. So this one will be the electric field when the R is 12. Alright. Alright, let's look at question 5. Okay, so this is the questions. So you have been given the rho V at different range. Okay, so here I would like to make corrections. Please change this one to 0. Okay, change this one to 0, yeah. Okay, and then change this one to capital letter R. Okay, so meaning that it will become like this, millicoulomb per meter cube. Okay, so now you have the rho V. So the rho V has different value at different range. In between 0 to 4, the value is 10 over R square milli. And then when the R is greater than 4, it is 0. So the structure is actually a spherical shell. Okay, it's a spherical shell. Oh no, it's not a spherical shell, it's a sphere. Okay, 0 to 4. Okay, so 0 is here and 4 is here. Okay, so now you have a rho V equals to 10 milli over R square. Okay, 10 milli over R square. Okay, so it is 0 when greater than 4, and you have to find the net flux crossing the surface. So the net flux crossing the surface, net flux is this, C, okay? It is also equivalent to the Q. So you need to find the Q when the R is 2 and the R is 6. Okay, R is 2 is over here. R is 2, maybe over here. And 6 is over here. Right. So let's find the Q. Okay, so the Q will be equals to integrate rho V dV. Okay, so when the R is equals to 2, it is less than the 4, right? Less than the 4. Okay, so over here we define our interval. Our rho V, we put it here. This is 10 milli over R square, and you have a R square sine theta dr d phi and d theta d phi. Okay, so the interval of the R will be from 0 until 2. Okay, because this is the point that you want to find the flux. Okay, and the theta will be 0 to pi, 0 to 2 pi for the phi. Okay, so you can simplify it. Okay, and you take out the constants, 10 milli, and also the sine theta. Then you integrate dr, d phi, d theta, and d phi. Okay, so you will get this term equals to 2. You will get 2 here. Okay, and for this term, okay, you will do it later on. You will do it later on. Oops. Okay, do it later on. So you take out the 2, it becomes 20 milli, and then 0 2 pi, and then 0 pi, and then sine theta, d theta, and d phi. Okay, so this one, you press calculator, will give you 2. Okay, 2, so you get 40 milli, and then outside will give you 2 pi. Okay, outside will give you 2 pi, so it will be 80 milli pi. So 80 pi. So it becomes 251.32. Okay, 251 1.32 milli. And this is coulombs. The unit is coulombs, right? The unit is coulombs. So this one is the flux crossing the surface when the R equals to 2. Okay, when the R equals to 6, what happened? R equals to 6. Where is 6? 6 is outside, it's over here. Okay, so your Q, okay, your flux is equals to the Q is equals to the triple integral. Rho V is the 10 milli over R square. And you have R square sine theta dr d theta d phi. Putting the interval, so the interval will be from 0 to 4, even though you want to find the flux at 6. But because the rho V only extend until 4, so you can just put the 4. Okay, so you will have a 10 milli, and then you will have a 4. Okay, then you have a 2, and you have a 2 pi. Okay. Two pi. If you do this is 2 pi. Oh yeah, it's correct. 10 times 4 times 2 times 2 pi. Okay, so it's equals to 502 millicoulombs. Right? So determine the D at 1 and also 5. Okay? So now this is question B. You have to find the D when the R is equals to 1. Okay, R equals to 1. Okay, so R equals to 1 is actually in these regions. In these regions. Okay, so look at the Gauss law. The Gauss law says that this is equals to the Q. Okay, so for the left hand side, we will have our D in the radial directions, dot with the R square, sine theta, d theta, d phi, the R directions. Okay, and the interval 0 to pi, 0 to 2 pi. Okay, this is at the left side. And for the right side, you can actually use this one. Okay, but replace with the R, replace the 2 with R. Okay, replace the 2 with R, meaning that, it would be 0, 2 pi, 0 pi, okay, and then 0 to R, okay, 0 to R, then you have a 10 milli, R square, sine theta, dr, d theta, and d phi, okay. So over here you will have a 4 pi multiply with 10 milli, and then you have the R. Okay, you have the R. And on the right side, you are familiar with the right side, is a d R square 4 pi. Okay, so you can cancel the 4 pi. Okay, and the D would be 10 milli over R. Right. So if when the R is equals to 1, okay, when the R is equals to 1, then you will get 10 milli. 10 milli, yeah? The answer should be 10 milli, yeah? Instead of 10 nano. Okay, we put in the directions. This will be the directions. Coulombs, huh? Millicoulombs. Okay, millicoulombs per meter square. Okay, so the answer should be milli, yeah? Okay, so we go to the next one is determine the D when the R is equals to 5. Okay, so basically it's the same thing, huh? You have the right side and also the left side, right? So for the R equals to 5, okay, so you have this. Okay, so the left hand side will be same thing, 4 pi, then you have the dr square, right? And for the left side, okay, you can just utilize this part that you have get it just now, which is this one. Okay, because the maximum will be until 4 only. Okay, so 502.6 millicoulombs. 1 millicoulombs. So the D will be equals to this 502.6 millicoulomb divide 4 pi r squared. Okay, in this case, the R, you replace it with 5. Okay, R replace it with 5. Okay, so you erase it and replace it with 5. So you will get 1.6 milli, okay, coulomb per meter square. So you have to do some correction on the answer. So it's the R directions. So this one will be the flux, the electric flux density coming out at the position R equals to 5. Alright, now let's look at these questions. For the potential difference, okay, you have 2-point charge, okay, that is the Q1 and Q2, and both are located at 2 different positions respectively, and now you have to find the potential at point P. Okay, so in this case we have 2-point charge, okay, meaning that we will have 2 sources of electric field. Okay, so for the potential at the observation point P, it will be the summations of the potentials due to the Q1 and the potential due to the Q2. Alright, so now let's look at the potentials of Q1. So for the potential of Q1, the equation will be Q divide 4 pi epsilon, and we have a R B minus 1 over R A. Okay, so as I explained earlier, okay, so the potential difference actually represent the difference of voltage between 2 positions, that is the position B and position A. So position A is a position at infinity. So in these questions, okay, we assume the V infinity is equals to 0. Okay, so we will not consider this part. We will just consider the RB. okay, the VB. Okay, right, so now to calculate the VQ1, okay, we take the Q1 equals to 2 nano, divide 4 pi epsilon naught, and RB will be the distance, okay, between the point P, okay, and the positions of Q1, 103. Okay, so you can calculate like this. So this one, so it will be equal to 0, -2, 0. Okay, so it will be equals to so let's calculate the answer. Is equals to 8.999 volt. Okay, so this one is the voltage, okay, contribute by the Q1. Then we go to the voltage contribute by the Q2. Okay, so this one will be Q2 1 over RB. Okay, we won't consider the RA. The RA is infinity. So here we'll have -4 nano okay, so this one will be 1 -23 minus -215. -3 2. Okay, correct, huh? So it will be -4 nano over 4 pi epsilon naught. So you have 9 plus 9 plus 4. So square root 22. Okay, so you put together. So -7.66. So the V total would be minus (1.33 volt). Okay, 1.325, approximate to that.